here we get to start talking about compounds and how to name and write formulas, and most of this should be reviewed, but I wanted to put it together so that you had something to go back and listen to with all of these different types of compounds together. So first, compounds are different elements, different atoms held together by chemical bonds. And there's two main types of chemical bonds, ionic and covalent, that we're going to be talking about here. And the differences in these is based on the electronegativity difference between the atoms that are involved in that bond. So our ionic compounds tend to have large electronegativity differences, and the covalent compounds have small electronegativity differences. And that large difference in how strongly the atoms pull on electrons in our ionic compounds is what allows those electrons to be transferred. Because one of the atoms is much stronger than the other, it pulls those electrons off. Covalent compounds are much closer in strength, electronegativity, so they end up having to share the electrons because neither atom is strong enough to pull them off. And then just some little reminders of what these diagrams look like when we did this with Lewis dot diagrams. We could start with an ionic compound like NaCl. We can see all of the electrons around the original atoms, and then they're transferred. We draw that arrow to show the movement of that electron, and after that bond is formed, we have the two differently charged atoms that are attracted to each other due to their opposite charges because they exchanged that electron. Our covalent compounds, we drew those lines between the elements to show they're being shared. The electrons don't belong on one or the other, they still belong to both. Now our CO2 that we see here has some non-bonding electrons involved. These dots are not involved in bonds. Those are just around those oxygens, but these double bonds here and here, single bonds, are that depiction of those shared electrons. So that's the fundamental difference between the two. Now let's just recap some of the name and formula writing stuff. Alright, so right here we're starting with our ionic compounds. In the names, remember that we are just going to leave the metal name the same, the first element the same, and then that second element, the non-metal's name, is going to change to having that "ide" on the end. So oxygen is going to turn into oxide, phosphorus turning into phosphide. That's the only change that we have to make in every single ionic compound. We do not add some of the other special stuff that end up going into covalent compound names. When we write these formulas, we're going to have to look at and check the charges and balance the charges. And there's a couple different ways to do that. My favorite way is cross, drop, reduce. But we're just trying to get the total charge in that compound to add up to 0, no matter how you go about it. Now, most of the time you won't have to worry about what goes first because we're going to be taking something like Na2O. We're just going to leave the elements in the same order. So don't get too preoccupied by that idea, but if I do tell you that an ionic bond forms between something like fluorine and calcium, maybe then you'll have to check what the charges are and make sure that that positive one always goes first. But for the most part, as long as you keep it in the same order as the name or formula, whichever one you got, then you're going to be right when you turn it into whichever one they want. So we have some special cases with these ionic compounds, and we'll talk about polyatomics a little bit more, but at the most basic level, even with a binary, just two-element ionic compound, most of those metals are just going to have one charge. We know those charges, that first group 1 and 2 metals, are just normal. But if we do have a transition metal, meaning a metal that has more than one charge, we're going to have to put a Roman numeral in the middle of the name in parentheses to say what the charge is, which means we're going to have to do a little bit of investigating to determine what that charge is. So let's do a couple of these examples here. I'm going to leave you a few of them to do yourself as well. So I'm trying to find the name of this compound, and names, we just name what we see. Sodium is Na, and then oxygen is RO, but oxygen is going to change to oxide in this final answer. So sodium oxide is the name of this compound. We could take a moment to check where sodium is to see if it's a transition metal, but it is in the first column, so it has only one charge, no Roman numeral needed. Now, when we're writing out a formula, we have to find those symbols and charges for these elements. Potassium is K, chloride is Cl, and then we have to find the charges. So the charge of K in that first column is a +1, Cl is a -1. Because these already cancel each other out, I don't have to do anything more. All I've got to do is put them together in that order, and that is our answer. We'll see a couple examples where we have to do more than that. Let's go down to writing another name. Here with ALN, Al is aluminum, and so that's going to be the first name. We never change the name of that first element. It is also not a transition metal. Aluminum is one of the few metals that has a set charge right over there near the middle. It's always a +3. And so no Roman numeral needed. We can go right into that N element, which is nitrogen. So we're going to start with that nitra prefix, but we take off the ogen and make it ide. So aluminum nitride. And then going down, actually, let's look at iron 3 chloride. So that has one of these scary Roman numerals in it, but all that's trying to tell you, if we're looking for our symbols for each of these elements, and then we need to find their charges, be able to figure out how many of each of them we have. Iron's in the middle. It does not have one charge. It has multiple charges, so we cannot predict its charge without that Roman numeral. That's telling us that the charge is a +3. So now that problem, these charges do not cancel out. So what I had taught you in the past, and what I use as the quickest, easiest way to find this formula, is to cross those charges over onto the other element and down to the bottom. Drop the sign so there's no more plus or minus sign, and that's going to get you most of the way to your final answer. And this is in fact going to be our final answer, just Fe1, but we don't write the ones in our formulas. Cl3. There are going to be some times where you might have to reduce. These are crossing, dropping every single time, but check if you need to reduce, meaning keep the ratio the same but make these subscripts smaller. Like I said, we can't do that here, but let's say that this first number was a 6. A 6 and a 3 could reduce down to a 2 and a 1. But since this isn't a 6 here, then this is our final answer. But just looking for a common denominator in any of those subscripts. Now let's try going backwards and finding some Roman numerals for a compound that needs them, because this is lead, and just like we saw before, O is going to change to oxide. But one of the things that I found when I was looking for lead is that it is a transition metal. It will need a Roman numeral here in order to tell everyone else what the charge of lead is in this compound that we have specifically. Because as you can see over here, we have a different type of lead oxide that is just ready and waiting to be used, but it's a different compound, so we have to put this Roman numeral in their names. I'll go ahead and write out this here because it's the same basic name. The only difference between these two compounds is what Roman numeral we're going to put in here. So let's do this one on the left together, and I'll let you do the one on the right. The way to figure out that transition metal is to use the charges we already know. So we're going to start at the oxygen side of things. That oxygen always and forever has a -2 charge. So if we just have one PB balancing out that one O, and we're asking ourselves what charge PB could have, then that has to be a +2 charge if the +2 and the -2 are going to cancel out and add up to 0, like we know they have to. So this is going to become lead 2 oxide, using those Roman numerals here. This is not going to be lead 2 oxide over here, but go ahead, work on those couple of examples you've got to do over here, and we will check them in class together. Now this last type of ionic compound that have polyatomics in them, you can tell when you've got one based on just the number of elements in that formula, or by looking at the end of a name. If it ends in 8 or ite, then that is generally one of our polyatomics. There are a few exceptions like our cyanide and our hydroxide in here, but for the most part, all of these names will end in ate or ite. And the process for writing names is the exact same as what we did with regular ionic compounds. We just name what we see. So we're going to start over here. And I guess we can just clear all of that writing off. Name what you see, except we do not have to change the ending to "ide" if that is a polyatomic. So in the example that we have here, we have ammonium and nitrogen together. So that's ammonium nitride. We did still change the ending because the ending element was not a polyatomic. On the other hand, when we see this next example, ZN3PO3, then this is going to be zinc. And technically, this is phosphite, not phosphate. You can see this is PO3, not the same PO4 that we have down here. I'm going to go ahead and pull up a few more examples here. This is from the back of your old periodic table with a few more examples. This still doesn't have phosphite on there. So we're going to be kind of seeing and exposed to a lot more polyatomics than you're going to need to memorize. And when it comes down to it, there's only probably about half a dozen that you might even consider memorizing, and all of them are already on this page. So as you know, your periodic table for the AP test does not have these listed out for you, and there's not going to be a specific question that's like, what is sulfate's formula and charge? But it will help with some questions and some types. So we are going to work on trying to memorize these specific ones that I put in your packet. Feel free to either use your previous packet, your previous periodic tables for a reference for a few more of them, or you're always willing and able to do that little bit of Googling research on your own. I'm not going to require you to use or know any more than what are right here. So let's get back to those examples. All right, so I made a couple little changes here just to make them a little more approachable with the materials I've given you. Here we have Ag, which is silver. And so that silver is with CO3 now, and I know that I changed that, but if we look, CO3 is just called carbonate, so that is going to be silver carbonate. Over here, writing formulas, just finding the symbols, charges, cross drop, reduce, just like before. We see potassium and carbonate. So carbonate is still that CO3 with the -2 charge because potassium is a +1 and these two charges do not cancel out. That means I am going to have to cross drop reduce them, bringing the 2 over, the 1 over, gets us K2CO3. And then ammonium chlorate. Ammonium is NH4 with a +1 charge. Chlorate is ClO3 with a -1 charge, and because those charges do cancel each other out directly, then we can just write those two polyatomics down without their charges. We never write charges in our final formulas, and that's that. Now, molecular or covalent compounds tend to be easier to name. It's a little bit more work to put into it, but it's a lot more predictable. So we use these prefixes that you see here on this page in order to describe how many of each element we have in a compound. So here when it says diphosphorus, well, phosphorus is P, di means 2, so that is P2. Trioxide, remember we do change that ending. Even in covalent compounds, that "ide" ending is still going to be in our name. And so we have to figure out what element that is, but hopefully we're familiar enough with oxygen to know that oxide is just O, oxygen, and that tri prefix means there's 3 of them there. So just remember to bring that prefix, which was before the element, around so that the number it represents is after the element's symbol. So still dealing with phosphorus and oxygen here, just changing up the numbers. Having 3 phosphorus is going to change this to tri-phosphorus. And then 8 oxygens is going to be octa-oxide. And that's really it. Just make sure to get a prefix before each element's name, and then we change that last name, that last element, into having the "ide" ending, just like with ionic. Now, if we do have one of a single element, like here you can see it just says carbon, doesn't say a number. That's because we do omit a mono prefix when the first element is just one of something. There's a lot of compounds where the first element is just one of something. So that gets rid of that pesky mono that would otherwise be kind of clogging up the works. So this is just carbon, and then tetrahydride means it has 4 hydrogens there. There is this note about dropping the A or the O. You can do that. You will definitely see things written like that. The AP exam proctors are not going to take off a point if you don't do that, or if you do that a little bit too much. It'd be better to just write the entire prefix and the entire element's kind of root name instead of leaving off too much. Now, acids always get a bad rap, and so we're going to talk about these a little bit more together. You'll see some on the other page, on the next page of practice that we're going to do in class, but it really just comes down to kind of like with ionic compounds, whether it's binary, just 2 elements, gives us a much simpler, straightforward hydro at the beginning, ic acid at the end, and that root element in between. So hydrochloric acid is just H and Cl, hydrosulfuric is just H and S. The oxyacids are where people's brains start exploding a little bit because we've got different types of polyatomics, but it's just based on the polyatomic's name. If that name ends in 8, then that 8 ending is just going to change to ic acid. So if there's sulfate, this SO4 ion, in our acid H2SO4, then that's sulfuric acid. If I had sulfite on the other hand, then sulfite changes to sulfurous acid. So one of our sayings to remember that is I ate a humongous bite. And that just helps you connect those 2 endings with how it's going to start on that polyatomic sheet and how it's going to end in our acid name. And when we're going backwards from those names, we just have to figure out, okay, if this is nitric acid, then I need to go find nitrate and just put an H in front of it. That's all that we've got for writing formulas. Find the piece that's going with the H. And we still are going to cross-drop reduce that, just like with our ionic formulas. And then we have some hydrates. Hydrates are going to use those same prefixes we saw for covalent compounds in order to tell how much water they have. And so this copper sulfate, and specifically copper 2 sulfate, has 5 waters on it, so that is going to be pentahydrate. So cobalt chloride, and that really should be something like cobalt 1 chloride perhaps, giving us a Roman numeral because cobalt is a transition metal. So we're going to write that formula, and then it says hexahydrate, so we're going to put a little dot to separate it. Hexa means 6, hydrate means water. So that is cobalt 1 chloride hexahydrate. Then aluminum sulfate, and that is a +3 and a -2. So I'm going to bring my 2 and my 3 over. Decahydrate, deca means 10, hydrate is water. BaCl2, using our ionic formula skills, that is barium chloride. Just focus on that first compound. And then 2 H2Os, the prefix for 2 is di. And then hydrate. Go ahead and give that last example a try. The next slide, or the next page in your packet, has a flow chart to help you differentiate between these. Everything but hydrates are on here. And next class, we'll spend a little bit more time talking and touching base on acids some, and we'll be working on these practice problems that you see here on page 11, in addition to finishing up the lab and doing a couple other little things. So take a look at these. Make sure you finish those examples from the previous pages. Come with questions if and when you have them.